So I just wanted to make a second follow-up video on this paper which we've recently published, and this work was a collaboration between myself and Silen and Arved at the Technical University of Chemnitz. And the paper is called Understanding Printed Hexagonal Contacts for Large Area Soil Cells Through Simulation Experiment. And the way it worked is they have this sort of, very fancy printing machine there at the Technical University of Chemnitz, where they can print very, very large area devices. So here, for example, these are strips that they're printing with a gravure and a flexo printer, and this is about 15 or 19 centimeters high, I can't remember, and about 5 centimeters long. So in terms of research cells, very, very, very big. And this is a layer of, I think, silver and then PDOT put on top of this. And then this could form the base of whatever printed device you want. So the game was with this paper to effectively try and understand these contacts and model them. So I think I described in the last video how, and this is a figure from the paper, how you could effectively discretize 3D shapes and turn them into effectively resistor networks. So this is the contact shape here that we're interested in. So you can see that sort of a row of these hexagonal grids. This is the 3D structure. This is it turned into just a resistor network, and this is a plot of resistance or calculated resistance of this structure. So imagine you put a probe of a voltmeter here and a probe there, and measure the resistance between here and here. This is the resistance you get at that point, and you can see there's a lower resistance here underneath the silver contacts, and resistance increases as you go away from the edge here, as you'd expect. So it's just like literally putting a probe between here and here. So I want to focus on effectively making these plots today. So what I've done is, if you look at the new simulations and click on large area hexagonal contact, you'll get this up, which is a demo example. It's similar to the one in the paper, but I'm not sure it's exactly the same. It's close enough. So if you click edit, you can see it's got this hexagonal structure. What we're going to be doing effectively is measuring the resistance between a place on the bottom here and a place on the top here. So if we click right button, and we can edit the type of the shape. So we might want to select maybe a slightly different honeycomb. So I'll select this one, and you see it's slightly changed. I think we're not going to play with this. We'll set it back to the one because I think that's better for our needs. So there we go. Now, what you can do is, if you go into the electrical tab here, the simulation tab, you see this thing called the scanning probe microscopy, and if you click on that, you'll be able to change how this resistance calculation is performed. So you see we're going to apply 1 volt between here and effectively all over this area here. We are going to perform the calculation on the whole device, so we're going to effectively scan over the entire device. We could perform it on a box section, or we could perform it on sort of an X section, or whatever you want, but that's how we're going to do this. We're going to scan over the whole device. So then what you do is, if you pop the simulation into SPM, or so scanning probe microscopy, and I've called it all because we're scanning over the entire device, and you click run. What it'll do is it'll take a little bit of time to do this, so I might actually just fast forward. That was quick. That was astonishingly quick. That was probably too quick. I think we selected something wrong. Oh no, sorry, whole device. There we go. I selected box section, which was just doing one section. So we want to select whole device. Run it. Now, let it go. There we go. Right. So it's going to take a little while. So you see it's chugging away here, and it's effectively scanning the device. So what I think I'll probably do here is just fast forward the video, so you don't have to watch this. But what I would say is that if somebody's using this sort of in earnest a lot in the lab, and this speeds a bottleneck, I can probably speed it up for you. With a bit more effort. So we'll just let it chug away here. Right, it's finished. So what we've got here now is we've got some files. We've got SPM, so scanning probe microscopy R, it's called X. And what this is a cut through of the resistance in the device. And as you can see, where's my picture gone? If I can find my picture. as you can see from this, the resistance effectively goes up as you get further away from this edge. So that's what this is. This is showing sort of increased resistance. And you see under the sort of the it's different, slightly different structure obviously, but under the wires, the silver wires, the resistance actually goes down a bit. So it's sort of this hump effect. So if we look at scanning probe microscopy _R, which is for resistance, it is effectively a plot of what's found in the paper. So there you go, something quite similar to that. So you can play around with this to your heart's content and figure out what the resistance will be of your own structures that you might want to fabricate in your device. Yes, I think that's it really. I'll just show you the circuit diagram of the device we just simulated. Just probably loading it. There we go. So that's the circuit diagram. You can see some of the, probably something to watch out for whilst I'm here. I'll say you can see this link here is broken. That means you're probably not meshing finely enough. So what I'd probably do there is just go to the electrical window and increase maybe the number of these points by a few, just to make sure it's all meshed correctly. So that's it. Thank you very much. I hope you find that useful, and yeah, I'll leave it there. Thanks very much.